Welcome to signal processing for millimeter wave communication for 5G and beyond. So, today we will be talking about the module 12, lecture number 60, that is the multi-user system or the MU system. So, in the MU system, how a beamforming can be used there and what are the consequences or what are the design challenges that will come into picture when you go for a MU system or a multi-user system. And the stuff which we will be covering is mainly the multi-user system and beamforming. So, we will continue the discussion from our earlier classes where we have the single antenna case, not single antenna, single user case, meaning you have only one user, one base station and one user. It is like a point to point communication, but now we will be graduating to multiple user cases. So, let me just define how a system diagram could be. So, you have the say base station here, you have the base station here, but what you have is you have multiple users here. Okay. So, you have user 1, user 2, probably I may have discussed it, but for the benefit of this talk we can. So, let us say I have k number of users here. Now, in a normal MIMO multi-user case, what will happen when there is no beamforming? I mean, there is no difference between that multi-user MIMO and the beamforming, except the fact that the beamforming will be entering. That is the only part. But if you have a multi-user MIMO, then what you usually do? Usually, in a mathematical sense, you have a stream of data. So, let us say you have this S bar, which can be a stream of data, and that within the S bar you can say some data may be for user 1, some data for user 2, some data for user 3 and so on and so forth. So, you have some. So, this block probably for the first user, this block probably for the second user, third users and so on. Now, this particular data, what you do usually, we do some sort of a pre-coding, right. So, you do a pre-coding over that. What is the purpose of pre-coding? The purpose of pre-coding, and it is mandatory, okay, because unless you do a pre-coding, you really can't do a multi-user MIMO very well. So, what you do there is that you have the precoder, say I do some precoder design, say P. So, probably and there will be multiple such precoders, right. So, every individual data, so let us this data, this data, this data can go through individual precoder and it will be something like a common. So, there will be P 1, say let us say S 1 blocks, and then there is a P 2 S 2 block and so on and so forth. So, this whole thing would be your the data that you would like to transmit. So, this is your TX data. This is a typical way of going through it. Now, when you receive it, what will happen? You have a multiple users, you have this multiple users here, and each and every user, say I have a different channel. So, this has a H1 channel, this has a say H2 channel, this has a channel number H. I am only talking in terms of the non beamforming case, but the same concept can be expanded to the beamforming case as well. So, if you have multiple such channels, what you usually do is that at the receiver. So, when you go to the receiver, so let us say I am for the user 1. So, what it will receive? It will receive some vector r, which will be H1 channel, but it will receive the complete data, right. It will receive the complete data, whatever is explained here. This whole data set will be will be there. So, let us call that as a R, or maybe say probably I call it X data. So, probably I will just say this is your X vector. Okay. So, this will be plus some noise will be coming there. Now, what will happen? Now, you do some sort of a equalizer, I mean usually that is the choice here. So, which means that once you receive it, each and every user will be going through a individual equalizer. So, which means at the user level you will have a equalizer W 1, W 2, Similarly, you have the equalizer wk. So, what is the purpose of this? The purpose is that once you receive it, then you just send an equalizer. I mean, you can pass it through an equalizer. So, what will happen? So, let us call it y. So, y would be some equalizer w 1 into r. So, that is typically the case. So, let us call it r 1 vector, but does it complete everything? So, point here is that what is so special about the multi-user? Multi-user is that this particular r will be having an x which will contain the data meant for user 1 as well as the data meant for other users, and that is the trouble. Okay. So, which means that this particular w 1 will be containing probably h 1 with the, I mean what I should say, the intended data. So, let us call it x 1 part, plus it will have h 1, x 2 other data part also, right, and this is your interference plus the noise. Okay. So, this R 1, whatever R 1 I just explained, that will contain the intended data h 1, x 1, plus it will have the interference data plus w, and this is the problem of every multi-user system. So, it is meant for one data, but it will other user data will also appear. Okay. That means your w, when I multiply it, it should be such that it nullifies this complete interference. It should be logically, right, because that is the purpose of my equalizer. Okay. Now, this w 1, whatever this interference is, will be, I am sorry, this would be w noise part. So, this whole part should be nullified, and that is one of the worst part. Okay. Now, how do you do that? There are theories and all. That means, this w 1 has to be, null, it has to reach in the, it has to be in the null space of the interference, and so on and so forth. That means, you can say this w 1 or this this equalizer multiplied by this I, this should be some sort of a null matrix or a 0 matrix, then only this interference can be. Now, there are many theories to do that, I am not getting into that, okay. But this is the fundamental part of every multi-user communication. So, this is the difference between a normal MIMO and a multi-user MIMO system, where where specifically a part of it, a part of the data will also be from the other users. Now, let us let us go back to my beamforming case. What happens to the beamforming case? Now, beamforming has an advantage. Okay. In the beamforming, the extra part that will be coming is the, in the multi-user beamforming, the extra part that will be coming is the addition of beamforming part. Okay. Now, beamforming inherently it has a certain advantage. For example, if you know, I think we may have discussed the MIMO case, where if you have a multiple such RF, you can create that many number of beams, right. So, which means that if my system is capable of a MIMO system, I can create multiple beams, right. So, probably this is one beam, this is another beam, this could be another beams, and so on and so forth, right. So, this is my transmitter, this would be my user 1, this would be my user 2, and this would be my user 3, okay, and so on and so forth as well. So, when it is a beam for multi-user beam, I have the liberty to send data to individual user, but there is a catch here. The catch here is that the system has a problem. What is the problem? Problem is that if you think of such scenarios, it does not really doesn't really I mean, you cannot get rid of the data meant for U2 and U3. For example, ultimately if you notice how a beamforming is done, so you have the data here, stream of data, right. Then it will go through W baseband at transmitter, then it will go through W RF at transmitter, and it will just piggyback it, right. And based on, if I have a multiple such, multiple RF chains, I can create as many, that many number of beams. So, now the point here is that because the data whichever you are seeing it, it goes through WBB. So, it means that if say I have say 10 users and I have 10 data here, but once it goes to the WBB, WBB is a matrix, right. If it goes through the WBB, the output here, it contains the data from every users, right. So, for example, I have 3 users or rather 4 users. So, I have 4 data stream. Let us say I am taking say one data stream meant for one user, right. So, this is my x1, this is my x2, this is, or rather I will put a different notation, S1, this is my S2, this is my S3, this is my S4. But once it goes through WBB, that is a matrix. So, let us say it is 4 cross 4, simple. Okay. So, the output is a vector, but now do you think the first element of that 4 cross 1 vector contains only data corresponding to UE1? No, right, because it is a matrix. If it is a matrix, the first element will be a function of linear combination of S1 to S4, second will also be S1 to S4, and so forth, right. So, which means that the data stream now contains data from each and every user. Okay. Now, you do beamforming after that, it does not really matter. You can do beamforming after that, and you can create say 4 split of the data, that is all fine. But bottom of the story is that each and every user will be having data for all the other users. So, beamforming only it helps to localize my power, but as far as the data splitting is concerned, it is really not helping us. So, we are coming back. So, this is also called a multi-user hybrid beamforming system. So, where I am serving multiple users at the same time, but the data that I am pumping, it's once it goes through WBB, it just mixed up. So, now I have the same problem which I just discussed. So, which means that once I am at a particular user, I also have to I get the interference from all of them. Now, given that, how do I design my beamforming parameters such that it minimizes my interferences, because that is the ultimate goal of every multi-user system. Okay. Now, let us I am just giving you a basic framework how it can be done, but exact solution probably it may take a long time to even find it, because that is like a one big papers and it explains a lot. I am just giving you the optimization framework rather, which will actually tell you how to how to do the beamforming such that this kind of multi-user scenarios can be tackled. So, let us do that. Okay. So, let us just generate the system model for it, and the system model can be say for example, I have k number of users. Let me just generalize it so that it will be easy for you to. So, k number of users. So, let us say I have data stream here and I have a data stream x k, right. Now, this I call it WBB, WBBT. Okay. Now, let us see how I can do the same problem, how I can solve the same problem here WRF. But now, you have every user. So, let us say for the first user. So, how now there will be antennas here, right. So, it can be NT number of antenna, and let us say I have every user, and every user has NR number of antenna. It can be heterogeneous also, like NR1, NR2 and so on, but just for our simplicity, let us assume all the users are having the same number of antennas. So, what is the first thing? So, like each and every users will be having the same set of blocks. So, you will also have a WRF, but it is at the receiver side. Then you will have WBB, at the receiver side and so forth, right. This is how for a single user case. Now, this is one user. Similarly, I will have here also the same thing WRF R. Now, let me put a different slightly different notation here. Let us call it comma 1 just to indicate that because for every users that WRF and WBB has to be different, right. So, you will have a different WBB and WRF. So, this is BB2R and so on. So, this is for user 2 and so on and so forth, right. So, that means the same data probably I can create a beam here, I may create a beam here, but it is only for channelizing my energy, but the actual inherent problem of multi-user is not really going away. So, it is still there. So, that means even in you channelize the beam, the data for user 2 will also appear in user 1. So, the problem remains the same. I mean, it is the same as your normal multi-user system problems. Okay. So, now how do you optimize such kind of things? Okay. Now you have a multiple such k number of such users that is coming into picture. So, let us just create a formulation, because I am only interested to know the formulation that can that can solve my problems. Okay. So, let us say the actual channel matrix whatever I will have it, let us say this is my channel matrix H 1. Now, this is my channel matrix H 2 and so on and so on. Now, what is this channel matrix? This channel matrix is nothing but your summation of I mean that is the same as what we have discussed earlier, alpha this let it be k just for your notational simplicity, then your array manifold vector of receiver and all these things, right, multiplied by, I think I have discussed enough about that. So, those things some k is there, some k is there, because there are k number of paths can be there in individual. So, that is that part is there. I mean, so that is the same channel. So, that means every individual beam will have their same channel model as we have just discussed so far for the millimeter wave. But now, so that part is clear. So, now how do I model it? So, let us say whenever you are given such kind of problem, I think we have discussed it, that you have to first come up with a cost function. So, you have to first, so what are the things that you need to find out? You need to find out WBB, you need to find out WRF. At the same time, every individual user, for every individual user, you have to have the WRF and WBB. So, that means so many parameters you finally have to find out, right. So, let us formulate the problem, because I am only interested in formulating the problem, not exactly the solving the problem, because solving the problem is a very standard method, it is a simple optimization methods, but formulating the problem is the issue. So, now when you are given such kind of issues, you first formulate a optimization problem. So, what is the optimization, on what basis, on what is the cost function, on what basis these parameters can be found out. So, let us say my cost function for this case, and you have hundreds of such cost function, is the standard MSE. Usually we love MSE because that is a kind of a 2 norm, and it is very convenient to solve. Okay, because moment you have a norm, 2 norm, you can do lot of things, like you can do lot of matrix manipulation, simple matrix manipulation, right. So, that is why norm is a very 2 norm is a very simple way to go for a optimization problem. So, we take MSE as our cost function. So, let us say how do I then solve it? So, now for that means I would like to have all these system all these parameter to be estimated in such a way the overall MSE of every individual users can be minimized. Now, if I just say I want to minimize for user 1 and I solve this problem, which is very good, but the only problem is that you get a WBB and WRF which is only meant for user 1, but that is not the case, right, because you have a common WBB and common WRF. So, now then it has to be some sort of a joint optimization. So, now I make the statement slightly changeable. I said that I would like to have a system in such a way that the MSE at every individual user, the summation or the total MSE if I call it, that should be minimized for all these parameters. So, instead of just considering MSE for a particular user, I call it, I would like to minimize the complete MSE of my all users, and that I call it j. Now, this is my cost function. Okay. Now, let us find out what is the MSE k. I think if you notice if you have gone through your earlier notes and all, it's very simple to find out the MSE for individual, right. So, what is the MSE? MSE for the kth user, what should it be case? The case. Now, look, it is the WRF and WBB which is coming into picture, but at the same time it will be the interference from the other data as well, right. So, let us keeping that in mind. So, which means that it is something to do with WRF k, then WBB, not k. So, this should be slightly changed, k, WBB k. So, that is your common W, then the data which is meant for meant for that particular user, let us call it say x1 bar. Now, mod of this should be minimized. Okay. Now, instead of x1 bar, I can just generalize it slightly, because I may not get exactly x1 bar, I will get the whole x first and then I am trying to minimize it. Now, this is for my, this is not the MSE by the way, this would be slightly modified. It will be x1 vector, this is the case, right. x1 is the vector meant for the user 1, that is all. So, this is your complete MSA formula, right. Now, you can get it, right. I mean, it is not so tough to get it. Now, you know what is x, right. So, x vector will have all your WRF T, WBB T, and it has the x1 vector, x2 vector, all these things, right. So, that has that. Instead of x1, I should say it is S1, sorry, because that is the S2 vector Sn vector. So, I will make a slight change here. So, this should be S, because that is the original data. Okay. So, which means that from here you will have two component, one part corresponds to the this part, another part corresponds to these parts, which is the interference part, but that is okay. I mean, I am not worried about it that, but whatever comes, something will be coming. I mean, right, I mean, how to solve this problem. Now, if I take an expectation over and above, you know how to solve that problem. Not solve, you know how, what is the equation of it, right. I mean, it is not so straightforward, it is not so difficult to get it, it is straightforward, okay, because we in our earlier classes, I have done it for a normal MIMO system, how to get an MSE formula for a normal vector and a MIMO system. So, probably this could be one of the assignment or an exercise from your side, what will be the exact formula for it. You just take it and you can find it out. So, I am not getting into the exact final formula of it, but let me just try to get into that. So, finally, what I will get into that is that I would like to minimize this quantity from k small k equal to 1 to capital K, okay. This quantity as such, expectation, I leave the exact equation for you to solve, Sk vector minus WRF k, W slight mistakes, WBB k, WRF k, x bar mod square. Probably I will correct the same problem here. Sometimes this is BB, this is RF, sorry. So, this would be BB, this would be RF. Anyway, so as long as you understand whatever it is. So, now this is your cost function. Now, you need to minimize this whole summation. So, minimize this whole summation over who are the argument. The argument, if you check it, obviously the argument will be WBB, WRF, where it will enter? It will enter here in the x vector, right. Then you have all the individual, you know, WBB and WRF, and for k is equal to small k equal to capital K. So, you can see this, but this is not enough, right, because you have to put some constraint. So, let us put some constraint. What are the constraints? So, first constraint is that I would like to put a constraint on my transmit power. So, who are the transmit powers? So, okay, fine. So, you know what is the, how to calculate a transmit power, right. So, this is the transmit power WBB T into your S vector. This should be the S vector. Yeah. So, mod of that, you can put an expectation, I do not mind. This should be some, you can put some power constant, you can put some more constant, okay. That is all fine, that is okay. And apart from that, this is the first constant. Apart from that, you can have some other constant as well, but usually you cannot solve this problem so easily, okay. Though I say that it is a matrix and all, actually it is a matrix problem. You see this expectation and all these things will be coming as a matrix format, right. But you can't solve it just like that. I think in the single case, I have shown you how to solve this problem with some sort of an approximation ideas. Who are the approximate ideas? One of the approximate idea was that this one should be 1, right. So, which means that WRF star WRF should be 1. So are okay. Similarly, if this is there, you can also extend it to individual user as well. Though this is not a constraint, but this is some sort of a, you can make such loose assumption, because this problem is tough to solve. If somebody gives you this problem, this is the cost function and this is the only criteria, and you solve it, this is not a very easy way to solve it, okay. So, to solve it, what you do? You put some additional restriction which can make your life simpler, okay. And these are the additional restriction. Put some additional restriction, then you will see that it is very easy to solve it, okay. I am not going into the exact solution, because solutions are dry. You can always look at the paper and see what solution they have taken it, but this is the more or less the approach, where even for a single case or a multi-user case, people have solved it, and this is also the way to solve it, okay. So, in summary, so how do you solve a multi-user, multi-user scenario is that so what is the ultimate goal? Goal is to ensure that your MSE is minimized, right, finally. And when you try to minimize your MSE, two things happen. You minimize the MSE, at the same time you have to minimize your interference, because that was the crack of the problem for multi-user system. Why? Because every user will be receiving his data as well as some other user's data, because of this problem, because of this WBB. It mixes all the data and send it to everybody, okay. So, that problem inherent, that is the multi-user problem. So, unlike in a multi-user system where I specifically design my WBB such that it minimizes the interference part, here a slightly different approach could have been taken, because here WBB is a common for all of them. So, what I do here is that we in general try to minimize the MSE. Now, what is MSE? Mean square error, right. Now, if there is if you say I want to minimize MSE, a natural tendency of the optimization formula is that it will try to minimize the interference as well, not guaranteed, but it will try to minimize it. So, here I do not put an additional restriction saying that this much interference I would like to, for example, in the multi-user MIMO, in a normal MIMO case, what what extra additional restriction we put? We said that your equalizer should be such that equalizer multiplied by your interference should be almost a 0 matrix. That was a restriction in a normal traditional multi-user case. It is very tough to solve such kind of problem, but people do that. But here I just slightly deviate it, but nothing stops you even from that kind of restriction also. For example, here you can put the restriction, here you can put one more additional restriction here, that WBB k multiplied by, calculate the interference from here, interference on the kth user should also be some sort of a 0 matrix, or you can say the trace of this mod square should be a 0. You can put such constraint, but the point is that it will be very complicated to come up with, because the reason is that you have too many parameters to solve, right. You have for each and every user you have two matrices you have to solve. So, when you have too many parameters to come, you really do not need this. I mean, if it is there, it is good, but you can still live without it. Okay. So, to counter the problem is that you just in general say I want to minimize my MSE. So, minimize MSE inherently ensures that this part has to be as minimal as possible, or the interference part. Okay. Now, this is a good way of formulating the problem, and I just leave it here, because formulation of a problem is more important than exactly solving it in an optimization framework. This is the classic way of representing a system. Okay. So, probably I will go back to my system here, and I will tell you what are the things that we have covered today. And this is a very classic reference, and the beautiful part of this reference is that this is the one which talks about the MSE based multi-user system. There are a lot of works where people take a different cost function, and it is a very complicated one. Okay. This is a very simple cost function. It is a letter, it is a 5-page letter. Please go through it, and you will see, or you can understand very simplistic part of the multi-user beamforming using a MSE. Thank you.